Okay, here's a clutch problem, like a bearing type problem, like we saw before. And as usual, the book is going to throw us an example, which is a curveball from what we've seen before. So let's go ahead and get this thing open. So this is the analysis we did before, and now we have this. It's going to be a curveball. So we have mu s equals 0.3, and we have a changing distributed load. It's more in the center than it is on either end, and it's triangular. So what is the moment we need to move the bar? Okay. Now, so the FZ minus 4 pounds and 1/2 times the 2 feet. The radius of the bar should be 2 feet. There it is. 1/2 times 2 feet. This is the triangular load. There's twice as many of it. So what is W naught? That's the first thing to figure out. So we use this equation to figure that one out. And we get 2 pounds per feet. So we have a triangular load of W equals there, 2 pounds per feet. That's the maximum. 1 minus x over 2 feet. That's the distance along the bar, the radial distance. And finally, we get 2 minus x. And remember, let's see, the units. Don't forget the units. The units are going to be pound per foot. Okay. The differential. So we still have to do an integral from 0 to r. And so we want to know at a distance of r from the center, what is going to be the normal force? Well, it's going to be W dx or dr, whichever you want to prefer. So now it's starting to look simpler, looking something like we can handle. And df is mu s dn, so we'll eliminate dn to get this. And let's see, dn, there we go. 2 minus x dx is dn. So here's 2 minus x dx, and here's the 0.3 for the coefficient of static friction. Differential moment is going to be distance from the center times df. We've already figured this all out. Substitute this into here, and you get this. Now, integrate from 0 to 2 of this expression. And we have to multiply this by 2 because we've got the moment coming out here, but we've also got, you'll notice df is in the opposite direction on either side of the bar, so we got to double this integral. Applied moment minus the resistance moment is going to be this. Straightforward integration now from here, from this step to here, straightforward algebra plus integration, and we finally get a result when you substitute x equals 2 of 0.8 foot-pounds. So it's just think through these problems. I mean, that I think is going to be the headline for thinking about these. Go back to kind of what first principles, how we derived them in the first place, and then repeat the procedure, which is what this is. This repeated the procedure for the disk. It's just instead of having a disk now, we have a bar. Okay, journal bearings. Now, the deal here is that the shaft, you're rotating the shaft, it's going to ride up until it slips. Until it slips at this point. So the reaction force has to be equal and opposite to the load. P is the load in this case. But there's going to be a distance here. And we can write an expression between N and F. So for a bearing, when a bearing will start to move, we would use the theta, the phi s, where it's already moving. We would use the K. With lubrication, phi K can be very small. And most of the time when you have bearings, you want them to move. So phi K can be quite small. And then we'll throw you a curveball. Next example throws you a curveball. Trying to look to see if there's anything else I need to say about this diagram. Okay. So we have a pulley. 100 millimeter diameter. Diameter, 10 millimeter shaft. Coefficient of friction is this. What will it take to get started? And here's T. What tension will it take to get started? So the moment, you're going to have a moment in the counterclockwise direction due to this mass, and then a moment due to the T. Okay. So what do you have to apply to raise the block and B, lower it? No slip between the belt and pulley, and ignore the weight of the pulley itself. So what we have here is, this is the point where it just begins to slip, and you can use that as the phi s. Let's go back here just to remind you that we're talking about this angle, the angle between the load and the normal is going to be phi. In this case, phi s, not phi k. So here's the load. Here's the normal, phi s. You're going to have RF you can calculate there. In this little diagram, it's right here. It's just this length. The distance between the line of action of the load and the line of action of the reaction. Okay. 981 newtons acting down here. What is the moment about P2? You are going to have a little RF going on. That's one of the points here. And so that's what part of this reasoning is all about. RF equals R sine theta S. We're taking sine theta S to be approximately mu S because it's so small. And what was mu S? 0.4. Arctangent of 0.4. I'd have to go figure it out. It's not that small, but it's also not that large. Okay. So we're using a simplification. So the radius of the shaft, that would have been the 5 millimeter shaft, right? 5 millimeter shaft. Oh, we're here. Okay, radius of the 5 millimeter shaft times 0.4, which gives us 2 millimeters. So this is going to be, well, there's the 52 that's where we get the 52 and the 48. 52 this way, 48 this way. Moment about P2, we're going to have T2. This T is going to be somewhat greater because this has a bigger lever arm, and 1063 newtons. Instead of 981 newtons, 1063 newtons. to get it going. Okay, voila, that's it. More exact. So here, 21.8 degrees, 1.86 millimeters. And again, you've just, instead of 2 millimeters, you use 1.86. And just get a refined motion. Now to lower it is just the opposite. You have it going in over here on this side. And the simple analysis again is this. The difference, it only takes 906 newtons to lower it. So you have to, T has to be much less. What is it, 75 newtons less? And then this moment is large enough to pull it in the counterclockwise direction. If T is this, let's see, 19 and 57 is 76. 76 newtons greater here, then you can start lifting it, overcoming friction, and then lift it. Okay, I think this is a good time to stop. It sure is.